Okay, welcome to the student project presentations for Fundamentals of Data Science course for Masters and PhD students at Uppsala University. Our first presentation is on network anomaly detection by Victor and Casper. Casper?
Yeah, my name is Victor.
And for this project, we wanted to do network anomaly detection. And network threats are major and growing concerns, you can see here. And from this video we watched from Spark Summit, you see that it takes an average of 191 days for a company to detect the threat, and then another 66 days to contain it. So it's a big issue and it's growing. And just an example is the WannaCry ransomware you see last year that spread rapidly, and it affected Uppsala University Hospital here in Sweden. So here's a screenshot of how it could look. And with better security systems and automated ways of finding these malicious activities, we could prevent these attacks. And we use this book, Advanced Analytics with Spark, from O'Reilly, to get the inspiration and find out how to do this. And they have a chapter on anomaly detection with the k-means clustering. And in that book, they use the KDD CUP 99 data, but it's quite dated and it's different from the data we've used. But it worked well as a proof of concept for our project. We got some inspiration from it. Yes, so here we can read something about anomaly detection. So that's the identification of items, events, or observations which do not conform to an expected pattern or other items in a data set. So something that's different from what you would expect, really. Now Victor's going to talk about the data collection.
Yeah. So what we're looking for is actually kind of unknowns, more or less. And to do that, we are not really sure what we're looking at or looking for. So to kind of collect our data, we try to collect as much data as possible, as well as doing some kind of attacking on our host. That could be like port scans or certain fingerprinting of the system, and that's not an unknown, but it's something to start with, and that's what we did. So we used Wireshark, which is a network package logging program where you can see all of the package flowing through the system, and we used Nmap for the attacker to kind of do all the port scans and the fingerprinting stuff. So our environment was consisted of the host and the attacker, so 2 computers. And from the book Network Security Through Analysis, we also got some inspiration and kind of tips on how to do this. And the data we collected needed to be anonymized.
Yeah, so we collected the data from my own personal network, so we don't want to publish that. That's some sensitive information, so we did some data anonymization, which basically means we anonymize the IP addresses and change them and remove the content from the packages. So we use this Python package called Faker, which generated fake source IPs and destination IPs for each packet. And so data anonymization is basically, it's for privacy protection. So you were, changing or encrypting the personally identifiable information. See here. So this is how we did it, basically. We install Faker. I'm not going to run this because we only have the anonymized data here. So we install Faker. Then you can see you anonymize each row. So basically just take the source, and then you set it to the anonymized version, and then the destination do the same.
And the data collected is in a CSV file.
Yeah. Exactly. So we just anonymize each row. So there's a one-to-one mapping for each IP address. So like the IP address X will always turn to Y for each mapping here. So we still get the same data, and we will get the same graphs and such, but the new IP address. And we remove the content from each, as they can have personal information there as well, which, yeah, we'll see later how we could have improved that.
Yeah. Okay. So Wireshark and Nmap. As I said earlier, Wireshark is more or less a network packet analyzer and a logging system, especially for like educational use and troubleshooting. So what we did was step by step, we opened up Wireshark, and logging traffic is pretty basic, but there's a guide on how to do it right here. So if you want to know how, just check it out. But we started a logging on the host that was being attacked. So all of the packets that was sent from the attacker to the host was logged by there and on there, and so we didn't go through by doing a man-in-the-middle attack and logging all of the traffic in the network. We started with just the host traffic. And what we did on the victim's computer was that we started a lot of stuff, because a lot of stuff is going on, and we wanted to have as much data as possible when we did this dump. So we started a Chromecast stream and music, and sending large files, and just a lot of noise, kind of. And then we started Nmap on the attacker computer, and started a port scan to kind of like, rain packages on the victim. And then we did a fingerprint scan, such as OS detection and software detection, and kind of different scripts just to see what was happening. And then we exported the Wireshark log as a CSV file, which can be seen here, how to do this. And this is our environment, more or less. So the victim computer, and this blue thing here is the Wireshark kind of area. So this is what the Wireshark is picking up, more or less. So no traffic from the attacker. If the attacker was playing some Spotify music or whatever, it wouldn't have been picked up in our dump, but we're just interested in the data that is for the victim, the network packages. Okay, and kind of like the structure of the data is, it has an ID, more or less. It has a timestamp from when the logging started. So for example, this was 0.001 millisecond after the data was, the network logging was started. This package was recorded, and it has a source IP of this and a destination IP. And then we have the protocol, and we have the length of the package. And we remove the information because of privacy concerns. Okay, so we've uploaded our data dump at this address. So we'll download this. It'll take some time. It's about 20 megabytes. And then our goal from here is to parse it into a table, SQL table, which we're doing right here. So we're creating a new SQL table called anonymized data raw, which is the data before we're really processing it. Okay.
Yeah, and then to gain some better understanding of our network, we wanted to visualize it as a graph. So the crash course in graphs, but they're made up of nodes or vertices. And these edges between them or arcs, you can see them as either directed or undirected. So which in here we can see node or vertex is like a destination or source IP, and then each edge is from which source IP and to which the destination IP. So we have a directed graph here for our network. So basically, yeah, it's just they send packets from A to B, then C, etc. And yeah, to do this, we use the Spark package graph frames. And yeah, here we stole a description of it from Rust. So it's a package in Apache Spark for data frame based graphs. It has an API in Scala, Java, and Python. And, yeah, and to visualize it, we use the JavaScript visualization package D3. So D3 is data-driven document. Yeah, but you can easily visualize anything really, and it's just plain JavaScript, so it's easy.
Yeah, so GitHub.io, oh, you haven't executed the framing function on that. First 7.
Yeah, so just use the user guide for graph frames. We're not using it. So. Here you can see how to use the graph frames. And we basically did this, but for our network instead. Yeah. And, yeah, so here we select everything from our raw data and display it, so you can see what Victor described earlier at the time. These are the anonymized source and destination IPs as well, the protocol and the language. Yeah, and here we're basically truncating the data. So we get the data for each millisecond, so we can basically group them together and see how many packets that were sent from each source to each destination during that millisecond.
Yeah, so we're grouping by source IP, destination IP, and protocol, and the new timestamp, which is based milliseconds.
Yeah, so here you can see that there were 2 packets from this source to this destination during that timestamp. Then we're basically visualizing it with the graph frames. So here we're creating the vertices, and here doing the edges.
And the count is more for performance reasons.
Yeah, so to visualize it, we're getting a huge amount of vertices and edges otherwise, so we're just taking where their big counts. So here you can see we're still getting bottom done. And, yeah, so here we're
So the counts is the number of events.
Yeah, during one
millisecond.
Yes.
It's still pretty big to show here in the notebook. We'll try. Yeah, so basically, I believe this one here, the lower one, is from the victim computer, and this one is from the attacking computer, I believe. you can basically see they have a lot of traffic here.
The typing computer.
Wait,
Mm.
no, it's probably just the typing computer. Should be somewhere here. And yeah, we can display the in degrees.
And this means that for each node, how many other nodes that are connected to it, right?
Yeah, and this is the out degrees. So.
Yeah. And why there's so many like inputs for each node is because we're having a lot of like, for example, we used the protocol data before, and we had the timestamps, and we had the number of counts and source and destination. When we're doing the graphs, we're removing the protocol and just calling it like the IP, and that's why we have this. Yeah, a lot of connected nodes, because we removed the protocol data when we visualize it.
Yeah. We'll have clustering.
Yeah. Okay. So what we wanted to do was kind of like cluster the data based on these and like attributes, and see how it was grouped more or less. And so the pre-processing, again, we rounded timestamps by milliseconds. We grouped the data by timestamp, source, destination, and protocol. And then we had a count of how many times these kind of packets was sent and received during that millisecond. Then we one-hot encoded the protocol values, and we added a link to describe the one-hot encoding if you're interested. And then we standardized the features for count and length, because we don't want it to be like a big number, because that would affect the k-means clustering a lot in ways we don't want it to. Yes. So what we're gonna do now is to filter out the features that are not numeric, for example, source and destination, IP, and yeah, we're gonna cluster this. Okay, so what we want to do first is to one-hot encode the values, kind of like turn all of the different protocols into columns, and then set the value to 1 or 0 based on for each packet. And we did not really succeed to do this in Scala, so we're doing it in Python. So we're selecting our data from the anonymized data table, which was the table with the group data based on timestamps. And here we're using scikit to scale different values, for example, length and the count for each. And yeah, so we're technically selecting the attributes that we want. For example, here we're doing the one-hot encoding for each protocol. I'll show you later how it looks. So we're pretty much taking each column and concatenating them to a new table. All right, and now when we've done that and stored it in an SQL table, we can go back to Scala, and to kind of like parse this for our own sake, we created a class, a packet class with all of the column names. So for example, this is what the table of one-hot encoded values look like. maybe we could do it like.
You may have 2% Python.
Oh, is it possible to do the display in Python?
I guess. It should be, right?
Done. Hello. Heyo, live coding. Okay, so this is what it looks like. So all of the protocols has been turned into columns and then turned into ones or zeros. Yes, next. And then we parse this data into Scala classes. And then so for each rows, we created an argument for the class, and then we parse this for each input we have. Did we run this? No.
Yeah, so here's where doing the clustering, we're removing the source and destination IP. And we're just clustering on the basically the protocols and the length and counts for each packet. So yeah, here's the list of the columns we're removing. Doing that and using the vector assembler for our training data. And yeah, so here we're running the k-means. And yeah, so we set to 23 clusters for some reason. And yeah, so we didn't actually have time to see if we could see the malicious activity in a cluster. So that's where we're at right now. And yeah, we have a bunch of improvements on the future work, so we're done with this. Basically, as you can see, we have a lot of fields here, so features, and that's quite a lot for k-means, which could suffer from the curse of dimensionality. So possible improvement for our clustering could be to use some dimensionality reduction, like PCA, or maybe use some other clustering mechanism that doesn't suffer from curse of dimensionality. And we could also see that we didn't parse the packet contents, so that was for privacy reasons, but we could probably get some further insights there, like the usernames, passwords, and see if it was, yeah, we'll basically parse the content and see if we cluster by that. And for our graphs, we could also look at like motifs there instead, and cluster on motifs possibly. So basically now we just showed it, so we could see that how it works. And we also saw this video here where they do k-means with the Spark streaming, so that with the network anomaly detection. So that could basically be when you just hook this up and keep it running on your network and look for malicious activity all the time. And oh yeah, here's this dimensionality reduction. Is when you basically remove features to try to keep the ones with the most insights, that get the most highest variance. And yeah, so here's Spark streaming for k-means. Yeah, that's it.
Are there any questions for
You look maybe a short remark. I don't think dimensional interaction is needed in this case because most of your dimensions are just these dummy variables that you introduce when encoding. So they are not. You don't get all these full degrees of freedom. You can think of this as just all of these together as just one dimension, but where the distance measure is just Hamming distance. Because I mean, the distance will always just be 0 if they are all the same, or 1 or 2 if they differ, right? So I mean, it's just some constant if they are the same protocol, or 0 if they are the same protocol. So I don't think that this should be a problem with K.
Also, there is this LSH variant, locality sensitive hash variant of k-means, which is super fast. And I think the book we were reading in a hurry of space set with 128 dimensions is still okay for k-means. I mean,
But
proper
this is a
dimensions.
performance question. This is, I guess, you were speaking about recursive dimensionality, and then it's a statistical question rather than a performance question.
Yeah. So what I mean is, even if you have completely valid dimensions, not just one encoding.
But then you need a correspondingly massive amount of data.
Yeah, of course. Yeah. But I mean, so the other thing I wanted to ask is, so you were playing with, or I guess you have parsed the data so that one could start interrogating with motifs using GraphX.
Yeah. Right. We could look for relationships like one graph is time back to this other, one node is time back to other node of other back.
Yeah,
Like
exactly. Because when you do your port scanning, for example, you will get some kind of motif patterns, right? Where, but currently your data, you don't have any tags that say you are doing this kind of attack, or anything like that. So, because if that were marked, for example, then you essentially have supervised,
exactly.
Supervised learning.
Yeah, but as they explain in the book in the top, they don't want to do supervised learning as we're looking for unknown unknowns.
Yeah, sure.
But
it would be nice to know if your unknown unknowns are picking up this like known things. Are there any other questions for? Okay, let's thank them again. Ready to go next?
Yep.
So, are you guys interested in internships and this type of stuff in the summer?
Oh yeah.
Sure. And what do you want? How much do you want to be paid?
minimum salary.
More than 0, I would say.
Okay, sounds good. So our next speaker is Joachim, but I'm going to turn off the video.
These are going to be online, right? So you can watch them later.
Yep. So our next speaker is Joachim Johansson, and he'll be talking about work on the Twitter data from the British election. And Joachim did a master's thesis in the math department.
Yeah. So as Russ said, I didn't participate in this course, but I did this project as a part of my thesis, and I wanted to investigate social media echo chambers. That was the main goal of the thesis, and I did 2 projects. One with Russ, which is the one I'm going to present now, and another one with David Hunter, who's also in this department. And just some background information. So an echo chamber is it's an environment where individuals only encounter other individuals with similar beliefs and opinions as themselves, and the views are reinforced by this. I mean, the alternative IDs are not considered. And the creation of these echo chambers online are mainly due to two different reasons. The first one is called selective exposure, where people selectively expose themselves to like-minded individuals. And the other one is something called filter bubbles, which maybe you have heard about. It's, for example, the algorithmically filtered content on, for example, Facebook. So, in my thesis, I presented two ways of investigating these phenomena on social media, or more specifically on Twitter. And yeah, this first part of my presentation is about the project I did with David, so I'm not going to go into the details of this. I will just keep it. Yeah, so this is the project I did last. So here I look at communication patterns on Twitter, where there's a person retweeting another, and it forms a network or a directed network. And I wanted to look at to what extent people with different ideologies communicate with each other on social media, and also I wanted to look if there are any differences in what type of information is shared among the people. However, the second question here, I didn't have time in the end to do that, so I only focused on the first topic. Okay. So we designed a Twitter collector utilizing the Twitter streaming API, and we collected for 10 days, 1 week before the election and 3 days after the election date. And we choose to look at 2,582 specific accounts, which are including members of parliament, political candidates, journalists, newspapers, political blogger, and other influential people on Twitter. We use these as key nodes and collected all the information from them and to them, which ended up being 5.8 million tweets from 1.1 million unique users, out of which 2.2 million were retweets. This is the timeline of the data collection. So the election date was on the 9th or the 8th, 9th, yeah. And the spikes here are the y-axis is the number of Twitter events, and there are three major spikes in this data. And the first one is during a debate between the major candidates in the UK election. The leader for the Conservative Party, Theresa May, and the leader for the Labour Party, Jeremy Corbyn. And the second spike here is a speech from the Prime Minister, Theresa May. And the third big spike there is the night of the election. And yeah, so when we did the data collection, we only collected everything in direct contact to these key nodes or key users. So in order to fill in the gaps, we also did some retrospective collecting where we found communication between active users, but that were not being tracked in the first streamed collection. So this we did retrospectively using REST API on Twitter. So here are some statistics. So the out degree is the number of times someone's been retweeted. The out neighborhood is the unique number of people retweeting someone. The in degree is the number of times the person has retweeted someone else, and the in neighborhood is the unique number of accounts the person person has retweeted. So as you can see, Jeremy Corbyn is definitely the most retweeted person in this data, followed by Alvin Jones, who is a journalist and blogger for The Guardian. Yeah, The Independent newspaper, some more newspapers here, and political bloggers and journalists. And as you also can see, Theresa May is not on this list. She's not very active on Twitter, which became a problem for this project actually. So if we filter out the politicians or the member of parliament here, you can see that Theresa May is still the second most retweeted member of parliament, but Jeremy Corbyn is quite more retweeted. And then there's some other, Lord Buckethead is actually like comedian, and but he's also participating in the election. Not really serious candidate. Some newspapers as well. The Independent is the most popular. So now we constructed a graph from this, a multi-edged graph where each edge represents a retweet, going from the retweeter to the person being retweeted. Or no, sorry, that way around. The edge is directed from the person being retweeted to the retweeter, symbolizing the flow of information. So what we did next was to map this multi-edge network to a weighted graph using the mapping you can see here, 1 over 1 plus the multiplicity of the edge. And this was to be able to use the Dijkstra's algorithm in order to find the shortest path in this network. And we wanted to find the shortest retweet path so that we wanted to find the paths that follow the most of the heaviest traffic with retweets. So for example, in this figure here, the shortest path will be from U through W to E instead of from U to B directly. And yeah, this is Dijkstra's algorithm, which is a way for an algorithm to find the shortest path in weighted networks, where you take the weights into account. All right, and then I got something like this, where each account is associated with a profile with degree of separations in this network to each of the some key accounts that I choose. I'll get into more detail when I show you the notebook. And so every person is associated with this profile, and we'll be giving ID on this based on the profile. And then I took the Manhattan distance between these profiles and constructed this matrix B. And from that matrix, I constructed this tree graph to the right, which is sort of a diagram showing the relationship between people of different ideologies, where people closer this tree are more closely related in terms of their ideologies, and people further away in this tree is further away. And I use this tree then later to see the frequency of retweets across these branches of the tree first, this is just the version of the tree. And you can see that the key accounts here are some politicians and some influential newspapers and bloggers. And there's like two interesting parts of this tree. We have first in the bottom, a branch with the closely connected to German carbon, which can be considered a labor ideology branch, and then we have some branches closer connected to Theresa May above that, with the degree of separation of 2 to 1 degree of separation to Theresa May, and yeah, also in the top there you see that there's one branch which is not connected to anything else but Theresa May, and this is yeah, but as you could see from here, Theresa May is not a big retweeter herself, so all the edges going into Theresa May's node is going to terminate there and not connect to any other parts of the network. So it's sort of closed subgraph of the network. So if someone only retweets Theresa May, then they're not going to be connected to anything else. Yeah. So yeah, and then I used the distances between the branches and looked at the frequency of retweets across branches. And I got this graph here where you can see that the distance or the frequency of retweets is heavily among people very similar or yeah, very close in this tree. Yeah. Yeah, I'm not going to show you the notebook as well.
So I guess the last figure is showing that the retweet, so that the ideological tree from your neighbor joining algorithm based on the Manhattan distance to all these, is it 10 different key accounts?
I think I had 13, but yeah, so
13 of them is meaningful in the sense that the leaf nodes that are close in the tree have a lot more frequency of retweets compared to the leaf nodes that are far away in the tree.
Yeah, exactly. So yeah, people closer connected in the tree are more inclined to retweet each other than people further away in the tree.
So the distributed Dijkstra algorithm works. I mean, yeah, because that's good. Picture is good, but yeah.
Okay, so yeah, I didn't have time to clean this up. So first I loaded the data that we collected from the Twitter collector, and I filter out, and also the augmented tweets, which are the retrospectively collected tweets I told you about, and filter out everything that is happening during the time of collection, because the retrospective data is everything that you can collect from Twitter, which is I think 200 pages or so. I
think 3,200 historical tweets. Yeah. But do you recall how did so you chose some accounts at random from the...
I choose, that's a good point. I choose the, where's the presentation?
Yeah, just go down.
So from the timeline, I choose people that were being active during these like spikes of events. So during the debate or during the night of the election, I figured that these people are going to be the most politically active. So I sampled people from these, like people that were being active during this time. For them.
And do you know roughly how many unique accounts?
I don't remember actually. Sorry. I think it's in the thesis. Mm. Um, yeah, so then I constructed a retweet network with the outpost user ID, which is which is the original tweeter, and the cpost user ID, which is the current or the retweeting user's ID. As the nodes. And here's the function to make the weighted network with the mapping 1 over the 1 plus the multiplicity of the edges. And then the Dijkstra's algorithm. I did not do this. This is by Ivan Sharikov. Yeah. So I constructed a graph using graph frames. And also wanted to check that everything is a connected component, which is basically this. This is the list of the components and the number of nodes in it. And as you can see, there are more than one component, but it's one that is dominating everything. So it can be considered to be just one big component. And here is how I define the landmarks. So I experimented with this to either use a data-driven approach, which would be good if you don't have any domain knowledge about the network. Then you can just find the most popular tweeters and use them as nodes or landmarks. But I found that the best composition was to just pick some users myself, because also with Theresa May, she wasn't one of the most influential tweeters, so she wouldn't otherwise have appeared, and she's quite an important person, so I wanted her in among the landmarks as well. So yeah, I ended up picking or choosing them manually. So I got the leaders for the different bigger parties, and some other politicians that are influential, and also some newspapers and bloggers that have a very political stance in writing. Yeah. Here's the table again with the most popular vertices. And if you filter out from the newspapers, you have this list. Do the same for under the politicians. Yeah, so this is where I actually run the algorithm. So for each landmark, I find the shortest path to each other node. And yeah, I'm not going to run this one, it takes a while. And here is the table with the degree of separation to each of the landmark nodes with respect to the shortest retweet distance, and the number of or the frequency of nodes that have this exact profile. So here,
the frequency of the population, all the nodes in your sample that have this
exactly. So 10% of all the nodes in my sample have this distances to each of the landmark nodes.
And I guess CS is the cumulative sum of these percentages.
Right? Exactly. Yeah. So what I did next was to, so I didn't want to use all the profiles yet because this is quite long. And so I used k-means and I used the 25 most popular profiles, and then I took the rest of the profiles and or I used these first 25 profiles as the centers in my k-means clustering, and sorted all the other profiles into these in order to reduce the size of the tree later. So yeah, it's a mess. Yeah, this is where I do k-means. So each account is going to be associated with a cluster being a profile. I don't think I have any more figures in which I want to show. Yeah, eventually yeah, so this is this here is the frequency of tweeters. So from cluster 0 to cluster 0 to another person in cluster 0, we have 7,271 retweets. So this is what I use to do to make the plot. Yeah, distances or the frequencies of retweets versus the distance in the tree. Yeah.
So so let me just try to understand. So you took the 25 most frequent profiles.
Yeah.
And then you use those as centers, initial centers for your k-means algorithm.
Right.
And then you took all the other individual profiles, the entire sample, and then tried to run a k-means algorithm with 25 cluster centers.
Yeah.
So that these will be somehow, initialized from the most frequent ones, and they'll sort of evolve. And then when the k-means algorithm terminates, you find the new cluster centers.
Yeah, but the new cluster centers are very similar to the initial ones. Yeah.
And so this way, you now have associated every single user, unique user, to one of the 25 clusters. Right. So it's a projection of the population ideological tree. It's a crude one, but still.
Yeah.
But then you get the pairwise distances like this.
Right. Yeah, exactly. Right. Yeah, any other questions?
So it's about the same thing, but what will happen if you start from 25 like random clusters? Because I mean at the beginning the k-means just pick like 25 centers, right? So
Yeah.
then if you compare both of them, because I mean there's this update that makes the center evolve every time.
Right.
So then you might whether converge.
Yeah.
So she wants to know if you just run the default k-means. Will that?
What will happen?
I don't know if you will get through this thing probably enough, but I wanted to use the initial. I wanted to use these as the initial centers because they represent the most frequent profiles. Yeah, I didn't try to just let it randomly decide. Maybe it would have ended up with a similar result since they are the most populated ones, and then will automatically reach closer to the center. So.
It's heuristic, as we all know, like even with the iris example, it screws up. Tilo, did you have a question?
I have a couple.
Oh, you have a question? Yeah.
So also about I have two questions. So first off, for the k-means, do you set some sort of weights for the points on how strong a pull they will have on this percentage weights? So that means the what do you call them, the signature? No,
the profile.
The profile.
Yeah.
A profile that has only like 0.1 representation in the population will have a stronger pull on the centroid as another profile with like a 10% representation in the population?
That shouldn't happen because he's using. Oh, I don't know. Oh, yeah, I see what you're saying.
Yes.
Okay. Yeah.
Right. So you just have your points
Yeah.
in space, and the centers will look at the closest points and move to the new center of those points.
Right. Yeah.
But since one of these points sort of represents 1 million points, and one of them represents only 1 point, I mean, in terms of users underlying the profile.
Yeah.
The one with maybe 10,000 users should have a stronger pull.
Yeah, that's right. But I use k-means on all the nodes. So if you're like, if the center is at where 10% of the population is going to be, then 10% will get close to that, or like they will end up there. So they will have a stronger pull on it by default, I think.
Oh, but you use the profiles as your data points, not the actual users.
As the initial points for the cluster, but I think you're using all the users.
All the users, yeah.
Not putting
okay.
the weights naively.
Okay. I thought you just did it on the profiles and tried to classify the profiles.
No, on all the IDs. Yeah.
Good. All right. Then you point the way. Okay. Second question is your tree you have had there in your slides. How do you create that?
Yeah, that's actually a good question. It's borrowed from
It's population genetics and phylogenetics literature. So it's just a neighbor joining algorithm.
Yes, but are you doing it? Or, because I know that if I remember correctly, this problem is NP hard, creating that tree. At least optimal.
Yeah, so I mean.
So I brought up, so we had this as an example in the course I have to teach. It's called phylogenetic supertree. That word is.
Yeah. Oh, phylogenetic supertree.
Yeah. That's basically what you're doing.
No, he's using the simplest possible algorithm. It's called neighbor joining.
Distance.
Yeah, it's a pairwise distance-based method.
Yes,
so
but that would be a suboptimal, like an approximation, right?
Yeah, it's just. I mean, approximation to what?
But it's not.
I mean, you can create an optimum tree, right? For your data, you can create what is the optimum tree in terms of distance between branches. This is an NP-hard problem.
Yeah. So an optimal tree, you need like every pair of nodes.
Well, it needs a measurement of
distance that is given by this pairwise distance matrix.
I guess. I don't know. I mean, you have to measure your objective function somehow, but you can measure it like in the branch, we put distance between them, and then for the next node, what's the distance between this?
Yeah. So just open up Wikipedia and hit neighbor joining tree. So I think this is after the Metropolis Hastings algorithm. This might be the most cited paper in the world. Very close to the top.
Yes, I actually think I know the author.
Oh, you know Sato and May?
No, okay. There's a Swedish guy who does this as well for one of the most cited Swedish papers at least, or
right. Yeah. So I mean, there's a lot of algebraic statistics done on this in Berkeley, for example. So but the idea is to go from a pairwise distance matrix to a tree that is close approximation to that satisfies this pairwise distance condition. And it's not, it's called distance method in phylogenetics, but it doesn't have a Markov model that shows how the characters evolve or anything like that.
Okay.
But we just chose that because there is an online thing you can pump the matrix and allow the tree.
Okay.
That's one main reason, and also there are fast variants of this that can scale to millions of nodes.
Yeah.
By making lots of even more cruder approximations.
Yeah.
That's only
Okay. So my question is basically sort of how important this is the. For me, there is an optimal tree, and you're approximating it, right? So for me, how important is that gap? That is sort of.
Yeah, that's a good question.
Do you get a reasonable result right now? Does the tree make sense?
I think based on my observation, it makes sense. Yeah, it's a good question. I didn't really take it into consideration, but
I mean, the constructor tree will just preserve these pairwise systems. So it chooses the closest two nodes and creates them first, and then it finds the next one, and it collapses the distance matrix sequentially.
Right.
So it's, if the distance matrix is true, then the neighbor joining tree is just a tree representation of this, right? But I don't know what you mean by the true distance.
So I mean,
true tree or whatever.
I mean, you will have. So that's a basically greedy algorithm for constructing these super trees or whatever they're called.
Yeah.
Right. The thing is, you can join two things.
Yeah.
And then you join them again.
Yeah.
But now the distance between these two.
Yeah.
Would be different than if you join. Like the other things.
Yeah.
Right.
Yes.
So, and there's a choice there, and the point is. So locally at the bottom of the tree, you will have the optimum distance between pairs.
Yes.
But then further up in the tree, you will have suboptimal distances
Yes.
based on your choices down here.
Yes.
Right?
Yes,
So
especially
by basically permuting things, you will have different sort of distances up in the tree.
Yes.
And there's one permutation which will have sort of minimum distance globally over the tree.
Okay, fair enough. Yeah. I don't know. I'm not an expert in tree algorithms. So, yeah.
That's what I mean. That often there's an ordering, which is not just the greedy joining things that are close, which will overall get you an even better value.
Okay, I see. So yeah, the optimal tree is the one with the right rotation, such that it's close as possible to the input distance matrix.
No, not the distance matrix. There's some. I mean, just because two things are close right now doesn't mean they are. How do you say it? Doesn't mean they belong. Okay, I'm saying if you want to do these, what's it called? Like in insects or whatever, if you have these trees of ancestry, right? Just because two things look similar doesn't mean you should put them next to each other.
That's a whole different problem. Yeah.
No, but it should be the same problem, right? Just because two people seem to retweet the same thing, kinda, doesn't mean you should maybe place them in the same next to each other.
Okay.
Because maybe that choice will affect sort of the higher up in the tree. How do you classify this subset?
Yeah. I mean, I don't know. Maybe we should take this offline. But yeah. I mean, I think you should just think of the neighbor joining. The way it's used here, it's just a visualization.
Okay.
Because all we are saying is, Theresa May's branch is on its own. It's in a separate clade, and all the liberal guys are on a completely different clade. It's making sense at that high level, right?
Okay.
I mean, we're not even doing any NLP or anything like that. Although the next set of speakers will be starting on some natural language processing, like the first steps. But if there are no other questions, then maybe let's thank Joachim. So should we do one more and then have a longer fika? Or do you guys want to have a fika and then do the fika first? All right, sounds good.
Before the watch.
Okay. Yeah, so after fika we'll have some of the NLP with Lee and Mariama, and then maybe Gustav on predicting solar radiation.
No, solar panel power generation.
Solar power generation, and then we'll have Yevgen and Dmitry go about hail population.